Hi all, in this video I want to talk about the addition of x2 to symmetrical conjugated dienes. x2 could be either Br2 or Cl2. In the previous video I talked about adding Hx, HBr or HCl. I also discussed how to figure out the major product by analyzing whether we want the kinetic versus the thermodynamic, but also determining which one is the kinetic. Is it the 1,2 or the 1,4? And which one's the thermodynamic? Is it the 1,2 or the 1,4 product? That video seen here, that's where I discussed those terms. I wasn't too pleased with how I presented them, so here in this video I just wrote it out, and we could just read off of the slide what we want to remember, or what our little voice wants to be saying to us while we take the exam. Let me show you actually on the document camera these three very important statements. The first thing to know or to remember whether you're adding Hx or x2 is that below 0 degrees Celsius the kinetic product is favored. At higher temperatures the thermodynamic product is favored. Now the kinetic is the one that's made faster, so this is, for my class, this is going to be always true. The 1,2 product is always the kinetic. It's always the one that's made faster. Now the tricky part is the thermodynamic product, the one that's actually more stable. It could still be the 1,2 product, but it could also be the 1,4 product. So again, the 1,2 product is always kinetic, so kinetic is easy to find. It's the 1,2 product. The thermodynamic, you want to analyze the stability of the product's double bond, and it could either be the 1,2 or the 1,4. Now, obviously, if the 1,2 and the 1,4 are identical, then, it's both. You don't really have a 1,2 or 1,4 product. You have both pathways giving one product, and we saw that actually in a previous video where two of the potential products were actually identical. But let's focus on this, and let's take our first reaction. Oh, actually, let me remind you what happens if we only have one double bond. So for instance, if I have this alkene, and I'll make it cyclic, when you add Br2, so this is from Organic Chemistry 1, when we learned about alkenes. We give a chlorinated solvent, CCl4. Okay, that's because if we run it under water, we get the halohydrin. And normally there was no temperature when we talked about this in Organic Chemistry 1, but you get the dibromide. And it's not necessary for what we're discussing now, but if you recall, it was anti-addition. But now we have a diene. Okay, so we are going to add two bromines, just like we did here on one of the double bonds. But we also have to think about the resonance of the intermediate. Now, I'm not going to go through the mechanism in this particular video. I want to show you how quickly to assess what the products are and how to pick out the major product. Oh, I didn't write it here, but the problem here is draw all the products and select the one major product. So let me recopy this. We have Br2, carbon tetrachloride as a solvent, and this is important. We're running this under very cold conditions, -78 degrees C. So right off the bat, we're going to say we're going to choose the kinetic product. So the temperature tells me, right, whether we want the kinetic or the thermodynamic as the major product. But the second statement says, oh, we're done. We know, at least we're done determining whether it's the 1,2 or the 1,4. The 1,2 is always the kinetic. So if I know I'm going for the kinetic, the one that's made faster, then for sure I'm going to pick the 1,2 product. Now, these dienes, both of them, I said they were symmetrical, and that means whether you choose double bond A or double bond B, you will get the same set of products. So I'll just choose double bond A, and the 1, 2, right, is 1 and 2. 1, 2. And you're adding the bromine on those 2 carbons. You know, this is a little bit easier to visualize because more easily visualized than adding HBr, right? Because with HBr, you have to remember that you're making the more stable carbocation by adding the H, in this case, on the end to put the carbocation here. Because you're adding 2 things. You're adding an H and a Br. But in this case, we're adding 2 Brs. So we don't have regio isomers, right? And this is our first product, and yes, this is the 1, 2 product, and it is definitely the kinetic. Okay. Now, how do you draw the 1, 4 product? Okay, I don't know if it's a thermodynamic or kinetic, but I do know that I have 1, 2, and I should have a 1, 4 product as well. If you think about it and label, this is the 1, 2, 3, 4, what happens is, again, I'm not doing the mechanism, but you shift the double bond, okay, over, and you have this. We're still going to get the 1 having a bromine, and now it's the 4, right? It's the 4 that gets the other bromine. So this is 1, 2, 3, 4. This is the 1, 4 product. And now we have to assess whether this is the thermodynamic or not. Look at the double bond. This is disubstituted versus mono. So look at the third statement. The thermodynamic or more stable product could be the 1, 2 or the 1, 4. We are determining this by the stability of the double bond. Okay, you could add that if you want. For these type of reactions with the conjugated dienes, this thermodynamic is determined by the stability of the double bond. So this is the thermodynamic. Okay, these 2 are not identical, so we'll draw both. Thermodynamic. And our major product is going to be low temperature, below 0. It's going to be the kinetic. So this is the major. Okay. So again, the temperature is telling you whether to go for the kinetic or the thermodynamic as the major product. You typically are drawing 2 products if you want to draw everything. You're drawing the 1, 2 and the 1, 4. It doesn't matter in this case whether we choose double bond A or double bond B, okay, because they would give the same set of products. And for my class, I don't care whether you draw the double bond as cis or trans. I'm more interested whether you could draw the 1, 2 and the 1, 4 and determine which one is the thermodynamic. There's no decision for the kinetic. It's always the 1, 2. Okay. For the second problem, we're above 0 degrees, so here we're aiming for the thermodynamic. Let's see what we get when we react this diene. Again, it is symmetrical. Chlorine. The chlorinated solvent here, it's just random, but I'll choose chloroform. What's important is the temperature. And our initial analysis, or our first thing that we should determine is, because of the temperature, we want the thermodynamic product. Now I don't know, right? I don't know if the thermodynamic is the 1, 2 or the 1, 4. It could be either. I have to wait till I draw the products. It doesn't matter whether I use double bond A or B. So I'm going to use double bond A, and if I use double bond A, we are adding 2 chlorines here and here. That is the 1, 2 product. And by default, or automatically, this is the kinetic. Now, the 1, 4 product is, again, if you need to label your carbons, you could label it as such 1, 2, 3, 4. Okay, we're still working with double bond A, but that double bond A could have resonance. And remember how we did it up here? You shift the double bond towards the 2, like right here. We shifted it toward the 2. So we have a new double bond here. Carbon number 1 still gets something, and then carbon number 4, right, gets the other bromine. So we are doing, or we are drawing the 1,4 product. This is 2. In both cases, right, the 1,2 and the 1,4, carbon number 1 gets something. It gets a Cl here, and carbon number 4 gets the Cl. So we have that product right there. My goodness. This is the 1,4 product. And now we have to determine the thermodynamic product. Because you are making both of these. You know, we made both of them up here, but we have a major and a minor. Do we have a major and minor over here? I didn't quite plan this out. Do you see the issue here? The thermodynamic is based off of the stability of the double bond, but both of them are di-substituted. So if I had to choose, so first of all, if I gave this on an exam, I would give them an option to say, well, both of them are equally stable, so both of them could be considered the thermodynamic, and they would circle. I would allow students to circle both. Okay, so we could do it that way. But if I'm going to force myself to figure out which one's more stable, I might probably just go with steric hindrance. And because these two chlorines are bumping into each other, right, they're bigger than hydrogens, I would rather have them more spread out. Both double bonds are di-substituted, so I can't use the degree of substitution as a decider. I would say this is the thermodynamic, so it does happen to be the 1,4, and I would maybe say slight major, or I'll just put major here. Okay. Now, like I said, because they're both di-substituted, I would write here, I would also accept that both are the major product. Or you could even say that both are the thermodynamic product. And ultimately, if you say it that way, you're claiming that they're equally stable. And based off of our knowledge of our rules of stability of double bonds, they are equally stable. They're both They're both di-substituted, but they're also both cis. Right? This is a cis double bond, same as that. So again, either circle both, or write down somewhere they're equally stable, hence there is no one thermodynamic product, or like I did here, I use steric hindrance as sort of a tiebreaker. Now, I think I'm happier now. I think I just had to write it out so I got the wording the way I liked it. But again, these are the three phrases, or the three things that the little voice should be saying in your head when you're working out not only, addition of x2, but also the addition of hx. These 3 points.